Okay, so when filling in your periodic table, one of the things I really want you to focus on and take some notes on are the different ways we refer to certain, sometimes it's groups, sometimes it's parts of certain groups, sometimes it's parts of a period, but there's classification among the periodic table. Okay? So if you're looking at your periodic table, this is one way to kind of look at how things are organized. Okay? This doesn't encompass all the different possible names, but I'm going to highlight many of the different colored areas on here. So, the first period, so it's 1 or 1A, so starting with lithium down, is called the alkali metals. Okay? Unique to alkali metals is these all have one valence electron. We'll get into more detail about what this means, but you may remember this from biology. The valence electrons are the electrons that can actually interact. They're the outer shell, and they're the ones that lead to reactivity of elements. Alkali metals are never found pure in nature. They are highly, highly reactive. And as you go down the group from lithium towards francium, the reactivity actually increases. For example, potassium, which is relatively in the middle of the group, has to be kept in kerosene because even just having it in the air, in the little amounts of water that would be in the air, potassium will react and react semi-violently with water. So, next group, the alkaline earth metals. Right, so this is group 2 or 2A. All alkaline earth metals have 2 valence electrons. Okay, so you'll kind of notice a trend here. Alkaline earth metals are less reactive than your alkali metals. They are still reactive enough to not be found pure in nature. Okay, so the alkali, or the leftmost group on the periodic table, is essentially the most naturally reactive. Okay? I wouldn't say it's the most naturally reactive, but it's more reactive than the alkaline. So as you go in, it gets a little bit less reactive. The word alkaline also gives the idea of being a base or basic. Okay, so most often you'll find alkaline earth metals in bases, so attached to hydroxides. And on the pH scale, they're going to be those things above 7, or really the things way up high at the 10, 11, 12, 13, 14 range. Okay? So the next part of the periodic table is there's a bunch of different types of metals. Okay? So generally speaking, metals are good conductors of heat and electricity. They're malleable and ductile, which means they can be formed, they can be bent. You can turn them into pretty much any shape that you need to, and generally without breaking them. Sometimes you need to heat them in order to do that, in order to be able to physically move them. Right? Most metals have high tensile strength, which means you can apply a lot of force to them without breaking, which is why oftentimes metals are used for building structure and things like that, because it can handle a lot of force and weight. Metals also have luster, which means they're shiny. Okay, they reflect light, so kind of like King Tut's gold sarcophagus. It reflects light very well, so it has luster. So the major group of metals are called the transition metals, and they fall in pretty much the dead center of the periodic table. Okay, these really fit into that grouping of what I described metals as before. Copper is a soft metal, so it's really easy to turn it into thin wire, to bend it, things like that, and it's a great electrical conductor. Most wires have copper on the inside, and that's what's conducting our electricity. Mercury is the only metal that exists as a liquid at room temperature. Mercury used to have lots of uses, like in thermometers and in a typical household use, but now we have found that it does have some adverse effects on the human brain, so it's not used as commonly in normal daily stuff, but it's still used in laboratories and more sophisticated controlled uses. Other metals include the inner transition metals. These guys are the ones that are off at they're pulled out of the transition metals and put in 2 rows down at the bottom. Okay? The reason for that is while these elements have similar electron configuration and some things in common with the rest of the transition metals, each group has some distinctly different trends or properties that actually make sense to pull them out and consider them as a separate group. Lanthanides are often referred to as rare earth elements or sometimes the heavy metals. And that is because a lot of them occur on Earth naturally in small amounts. Most of the time they're created through nuclear reactions with a combination of other elements. Actinides are different from all the other transition metals in the sense that they are all radioactive and react very easily with nonmetals. Okay, so they are still transition metals. They're just separated because they have some unique properties to their own period versus the rest of the transition metals. So the post-transition metals are this kind of, it's not a period or a group, they're just kind of a chunk of elements that are located between the main group of transition metals and our metalloids. Okay? So these metals are generally softer and actually more brittle than the other transition metals, so they are not as malleable or ductile. They tend to break more often as you try manipulating them. They also typically have lower boiling points. And these metals generally form covalent bonds more often than metallic bonds, which we will get into the difference, but that gives them different chemical properties. Then another, this isn't a period or a group, but another kind of chunk of elements that are called metalloids, and they border those post-transition metals and nonmetals. Okay, and they have properties of both metals and nonmetals. Metalloids are more brittle than metals, right? But they are less brittle than nonmetals. Okay, so they're kind of in between as far as brittle. Metalloids are semiconductors of electricity. And some metalloids have luster or are shiny, and then other ones aren't. Okay. One really useful metalloid is silicon. It's shiny, it has a luster, and it is brittle like nonmetals. But the key thing is how it is a semiconductor. If you've ever heard of Silicon Valley and the reference to that in any way in reference to computers, silicon is the main metal used in semiconductors and computers and many electronic equipment. What it does is while it's a semiconductor, so it doesn't conduct electricity quite the same way as, say, copper, it can conduct the electrons that move in the electricity actually faster, which allows for computers to have that incredibly fast response time and, supercomputers to take massive amounts of information and data and apply algorithms to it and solve problems much faster than humans. Okay. Then the other metalloids are as listed, and they just kind of form a zigzag between the metals and nonmetals. Alright, so our unidentified, these nonmetals don't have a more specific group, but carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium are. Nonmetals are poor conductors of heat and electricity, so they often are not found, or they're more used as insulators. They tend to be very brittle, alright? You're not going to be able to bend them and make things up. Many of them are gases at room temperature. And a good example of this is carbon. So if you think of the graphite in your pencil, or if you've ever used the mechanical pencil and the pencil lead, that's an example of a nonmetallic element. Alright? It's not magnetic, it breaks really easily. Okay, you can't sit there and take the pencil lead and, fold it into, a heart shape or something like that. Some other examples of nonmetals. Sulfur. It used to have a name of brimstone. It's this kind of yellow brittle rock. It's very easy to just kind of crush it in your hands. Microspheres of phosphorus have been used as a reactive nonmetal. Then carbon actually has several different forms, graphite being one of them, but diamond is also a form of elemental carbon. And if you've ever seen a colored diamond, that's because there's something else that's been caught inside the carbon atoms to reflect a different color. So the group 7A or 17, so the second to last column on the periodic table, is called the halogens. Halogens, we get kind of back into our valence electron trend, all have 7 electrons. That's something they have in common. Halogens are never found pure in nature. They are too reactive. Alright, so these are kind of at the opposite end of the alkali and alkaline metals. Halogens in their pure form are diatomic molecules, which we've already talked about. Instead of being singular fluorine or chlorine atoms, they always form pairs that are covalently bonded to each other. Then an example of a halogen is chlorine in its natural state is a poisonous gas, but when bonded and used in another form, chlorine can be used as a disinfectant, like in the pool water. Alright, the last column, so group 8A or 18 of the periodic table, is known as the noble gases. Noble gases have 8 valence electrons, with the exception of helium, which only has 2. But essentially that means they have full electron outer shells. So they have all of the electrons that they want. Noble gases are only found pure in nature because they are chemically unreactive. Because they have full valence shells, they don't need to react with other elements and atoms to fill up their shells. And then, because of this, noble gases are generally colorless, odorless, unreactive, and due to that, we're actually one of the last of the elements to be discovered because they don't react with anything, so you have to actually find them in their pure form. So, that is the classification of the periodic table. You will need to recognize where these groups or sections of classification begin and end. You'll want to know the main things that they have in common. Okay? And when you take the quiz, you'll see the kind of questions that I might ask you. Okay? But make sure you take the online quiz, and I'll see you in class.